Welcome to section 3.5 notes, where we will talk about implicit differentiation. So we know what differentiation means. It means derivatives or taking the derivative. Implicit is something we will have to define, and we'll define it as opposed to explicit. So we will indeed first see how to distinguish between functions that are written in implicit form and explicit form, and then we will learn how to differentiate when a function is written in implicit form. So a relation is defined explicitly when y is isolated on one side, and that's the functions we are used to see, like y equals 2x minus 5, y equals e to the 5x squared. Anything that starts with y equal and x's are on the other side, that is explicitly defined. A relation is implicitly defined when y is not isolated. So for example, here 2xy minus 5x equals 8. You can see that y is not on the left side with all the x's on the right. Or here xy squared plus sine x equals y plus cosine y. We have y's in many different places even. So sometimes, like in the first example, it would be possible to manipulate this relation and make it explicit. We could move the 5x, we could divide by 2x, and then we would have y equals 8 plus 5x over 2x, and that would be defined explicitly. In other cases, like here, I just tried to make it complicated. You have y squared, you have y, you have cosine y. There's no way in the world that you're going to be able to put all the y's together, factorize, and get y equal. So this is bound to remain implicit. Implicit differentiation is therefore the process by which we take derivatives on both sides when we have an implicit relation. So for example, here, y squared equals x. This is implicit because it's not y equal. We could write y equal plus or minus the square root of x, but that's not the purpose right now. We're trying to practice with a simple example how to take the derivative implicitly. So y squared equals x. And in fact, you may realize that this is not a function, because if I choose a certain x, like 3, let's choose x equals 9. If I choose x equals 9, there's actually two possibilities for y. I can have y equals 3 or y equals negative 3. Both of them satisfy this equality. So y squared equals x is not a function. If we sketch it, here's what it looks like. And you may remember that a function needs to pass the vertical line test, which means if you draw a vertical line, you need to have only one value on the function. But here we have two, and that is translated algebraically as if I choose a certain x, there's two possible values for y. Y can be 3 or negative 3. However, even though y squared is not a function, the slope is defined everywhere. In fact, it's defined almost everywhere. Here there's a slope, here there's a slope, and these are the slopes we're going to look for. Here there's a slope. The only place there is not a slope is at the origin. So the slope is defined at every point except 0, 0, or except the origin, because there's a vertical tangent. Because the slope is defined everywhere, we should be able to use derivatives to find what that slope is. And this is what we're going to do in this first example. So use implicit differentiation to find the slope at the points 9, 3 and 9, negative 3 on the graph. So when you take the derivative of an implicit relation, the way you take the derivative of x is no different. So here the derivative of x is 1. On the other hand, when you take the derivative of y, something changes, because we're taking the derivative of y in terms of x. We're taking a derivative in terms of x. So the derivative of y squared is 2y, but then you have to multiply by y prime. Why is that? That is because y prime is the inside derivative. We don't know what y is. In fact, in this simple example, we could know y is plus or minus square root of x, but it's something bigger than just the variable. There's a bunch of stuff in this y. So if we want to take the derivative, we need to take care of the outside first, which is the square, and then we need to take care of the inside. So why is this? Oh, yeah. So first we'll take care of the square, which is why this becomes 2y, and then we multiply by the derivative of the inside. And we don't know what it is. What is the derivative of y? We don't know, so we just write it as y prime. From here, all is good. We can solve for y prime, and we get that y prime is equal to 1 over 2y. That might be a little funny for us because we're not used to doing that, but if we want to find the value of the slope, we will just say, okay, y prime will give me the slope. At the point 93, I'm going to have to substitute in this expression. There's no x's, but I can substitute y because it's the point 93. So y prime equals 1 over 2 times 3, that's the value of y, and I get that the slope is 1 over 6. 1 over 6, so it's going up, and we can see if I drew a tangent line that it is going up slightly, so 1 over 6 seems reasonable. What about the slope at 9, negative 3? I'm going to plug in a y in here again, but this time y is equal to negative 3. And I get that the slope is negative 1 over 6. So there's a symmetry which we can see about the x-axis. If the tangent line here goes up by 1 over 6, then it seems reasonable to agree that the slope here is going to be negative 1 over 6. It's a line that goes down slightly this time. So, sorry about that. Here's an example that's a little bit more complicated maybe, but we'll see that as long as you remember, here's a key, you have to remember when you take a derivative in terms of x, but you're differentiating another variable, you have to multiply by y prime if the other variable is y. And this is the advantage of using this way of writing derivative. dy dx tells us that x is the variable we're differentiating with. So what's the derivative of 2x? It's 2. What's the derivative of x squared? It's 2x, no problem. But what's the derivative of sine y? It's cosine y times the inside derivative, which is y prime. Okay, so x is the privileged variable here. It's the variable that we differentiate with. All other variables would have times inside derivative attached to them. From here, y prime, we can gather it on one side, so we just do minus 2x and then divide it by cosine y, and we get the answer. This should be a y. And we have the derivative. Okay, here's a bit of a more consequential exercise. Find the normal to the curve x squared minus xy plus y squared equals 7. We don't know what this curve looks like, but it's definitely explicit. Maybe we could solve for y, maybe not. It might be difficult, not sure. What we're going to do is we're going to use what we know about implicit differentiation. What does normal mean? Normal means perpendicular. Okay. So we're looking for the perpendicular line to that curve. It's perpendicular, not tangent, so we'll have to tweak a little bit in the end. When we know the slope, we'll have to take the inverse reciprocal. So, what's the derivative of x squared? It's 2x. What's the derivative of minus xy? Well, here's an example of a moment where you have to remember this is a product, so I have to use the product rule. So we'll put the minus first, and then we'll open a parenthesis and take care of this product inside the parenthesis. So u is x, v is y. If I do u prime v, I'm going to get 1 times y, plus u v prime. So what's the derivative of y? It's 1 times y prime, or you can just, well, by definition, the derivative of y is y prime, so it becomes u prime v plus u v prime. Then, what's the derivative of y squared? That is 2y times the inside derivative, so 2y times y prime, equal, finally we have the derivative of 7, which is 0. From here on, we're going to want to clean all of this up. These are a few steps of algebra. We distribute the negative in front of the parenthesis, and then we factorize y prime. You can see that there's a y prime here and there's a y prime there, so I factorize them, and from there it's easy to solve for y prime explicitly. So we get y prime equals y minus 2x over 2y minus x. So what is the slope at the point negative 1, 2? I'm going to plug in x equals negative 1 and y equals 2 into my derivative, and what I get is that the slope of the tangent line is 4 over 5. Now that's the slope of the tangent line, but I'm looking for the normal line or perpendicular line. So how do I do that? I flip the numerator and denominator, and I change the sign, so the perpendicular line's slope is negative 5 over 4. And now we're done. We can just use the line point slope form, so y minus 2 equals negative 5 over 4 times x plus 1. Here's a sketch of what this actually looks like. So we didn't know it, but in fact this equation that we saw was a tilted ellipse. And here's the point negative 1, 2, and we were trying to find the perpendicular line at that point to the curve, and so this is what we had. Okay, now we've learned about implicit differentiation. We're going to combine that with something we've learned earlier, which was finding higher order derivatives. In this example, we're trying to find y double prime, so the second derivative of y. And again, there's no shortcut. We have to find the first derivative and then take the derivative again. First derivative of 2x cubed is 6x squared. Derivative of negative 3y squared is negative 6y times y prime. Just always remember that this implicit differentiation requires the inside derivative for all variables that are not x. Equals 8, so the derivative of 8 is 0. And now we can solve for y prime. Y prime equals negative 6x squared over negative 6y, and it cancels out nicely, so y prime equals x squared over y. From here on, I'm going to take the second derivative, so ignore this part now, because we're just focusing on y prime equals x squared over y, and that's a quotient. So let's use the quotient rule. We will have u equals x squared, v equals y. This is a good exercise for you to do. We have y double prime equals u prime v minus u v prime over v squared. Excellent. We're done. Well, not quite. If you notice, someone has been trying to sneak into the party, but they were not invited. Can you see where? Yes, indeed, y prime. We wanted to find y double prime explicitly in terms of x and y. We don't want anybody else. And here's y prime, so we need to solve that little problem. And the trick is, we know what y prime is. Y prime, if you look back here, is x squared over y. So we can substitute that. It's a very neat trick. And here's our final answer. Y double prime equals 2xy minus x squared times x squared over y squared. There's clearly some little things we could do to simplify that, but it's not really necessary in this situation. Lastly, something we saw in the previous section, but it's worth looking again, and I think it's a really beautiful proof. I think we all like music, most people like video games, but if you appreciate proofs like this, then maybe you like math, and that's a little bit more rare, so you're a little bit more special if you like these kind of things. So value it. Y equals ln of x, we are trying to show that the derivative of y equals ln of x is 1 over x. That's what we saw last class. To do that, I'm going to switch and take the exponential function on both sides. So I get e to the y equals e to the ln of x. And as you know, e to the ln of x cancels out and it's just equal to x. The great thing about that is twofold. Firstly, we know how to differentiate e to the power of something. And secondly, we've just learned right now how to do implicit differentiation, so we can take the derivative of that now. the derivative of x is 1, and on the left side the derivative of e to the power of y is e to the power of y, that's the derivative of an exponential, times the inside derivative, which is y prime. And I divide by e to the y, so we get e to the y prime equals 1 over e to the y. That's the answer. However, we would like to have this in terms of x, and look at row 2 here, e to the y is actually equal to x, so I can substitute it back here, and I get y prime equals 1 over x. There we go, that was it for section 3.5. Thank you so much for listening.